Hello, welcome back to the channel. So let's continue our previous discussion on convergence test and check whether whether this definite integral converges or diverges. So now in order to check whether this integral converges or diverges, you can also use limiting comparison test in order to check whether this integral diverges or converges, and that would be a much easier way. But in this video, we'll solve this question using a new concept which is about removable discontinuities. So that is why we'll solve this question using a different approach which we didn't cover in the last videos, but you can always use limiting comparison test to check whether this integral converges or diverges. You know that for your g of x function assumption, you'll take the you'll take the behavior of f of x for large values of x, and clearly you can notice that your g of x will be then x upon x square, which is 1 by x in that case, right? But now, since we are learning the concept of removable discontinuities in this video, so we'll use it using a different approach. So you can clearly notice that in the denominator, since we have a quadratic expression, we can factor this out, right? And if you'll factor this out, you'll notice that x square minus 11x plus 10 can be easily factored out to, so this integral will be 0 to 10 x minus 1 dx, and the denominator will then be equal to x minus 1 into x minus 10 in this case. So x square minus 11x plus 10, if you'll factor this expression out, you'll get x minus 1 times x minus 10. And now in this integral, you can clearly notice that this function is not defined at x equals 1 and also at x equals 10. But we can cancel x minus 1 term in the numerator and denominator, which is the point where we will cover the concept of removable discontinuity. So whenever you have this situation, when you have the discontinuity point expression in the denominator and also the same expression in the numerator, you know that we cannot straight away cancel these expressions, right? Because in order to cancel x minus 1 in the denominator and in the numerator, we have to ensure that x is never equal to 1, right? But in this case, since we are calculating the integral, this is known as removable discontinuity. So since this is the case of integrals and we are talking about removable discontinuities, in these type of cases, you can totally cancel these two expressions. So in this case, even if we had an x minus 10 term in the numerator, we could have easily cancelled that x minus 10 term in the numerator and also in the denominator, because that is known as a removable discontinuity. And the reason why we do that is, basically, let's assume a simpler function. If we assume a simpler function which is simply x minus 1 upon x minus 1, and we are calculating the integral of this expression over here. So if we are calculating the integral of x minus 1 upon x minus 1, let's take the same limits from x equals 0 to x equals 10 dx. You know that this function over here is not defined at x equals 1, and you also have x equals 1 in the interval over here. But since in this case we are calculating the integral in this case, this x minus 1 expression becomes a removable discontinuity term. So since this is the case of a removable discontinuity, cancelling it will not affect the integral, because if you'll sketch this function on the graph, so let's sketch this function, and if we sketch this function, you know that this function is basically equal to 1 where x is not equal to 1. So if you'll sketch this function from x equals 0 to x equals 10, you'll get a straight line from x equals 0 if this is x equals 0 and if this is x equals 10, but at x equals 1 you'll have an open point, right? So it will be an open circle point over here, because at x equals 1 our function is not defined. But since in this case we were dealing with calculating the integral of this expression, which is calculating the area under the curve of this expression, we can clearly notice that removing this point does not affect the area under the curve for this expression over here, right? So that is why in the cases of removable discontinuities, you can cancel these expressions, because cancelling these expressions will not affect the definite integral. So that is why in the original function integral expression, if we copy this down, again, since this is a removable discontinuity, we can cancel these terms, because these terms in the integral will not affect the integral at the last. So this integral will then be simplified to basically calculating the integral from 0 to 10 of dx upon x minus 10. And now we already covered the concepts of solving these type of questions in the previous videos. What you do is basically you take limit a approaches to 10 minus 0 to a dx upon x minus 10, and then if you'll solve this integral expression and take the limit, you'll clearly notice that this limit will not exist, which means that our original function diverges in this case. And if you'll also confirm it using limiting comparison test by taking g of x to be 1 by x, you'll also prove that the f of x dx integral, which is this integral, diverges via the limiting comparison test as well. So that is a confirmation about the solution to what we discussed in this video over here. So that's it for this video. In this video, we covered the concept of removable discontinuities, and the main takeaway from this video is whenever you have a removable discontinuity, you can cancel that expression and it won't affect your original definite integral. So that's it for this video. Again, feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.